the determinant of a matrix. This chapter concerns the determinant of a matrix and also the many applications of the determinant that can be applied. You will see that the determinant, its application, is rich. First, the definition for determinant. Let a matrix be a square matrix, say, for example, A. Then we associate with each square matrix a scalar, that is a number, that we call a determinant. We denote the so-called determinant by det of A, or we can use for example here, or we can use, it looks like the absolute value but it's not. That denotes the determinant. Also, we can put the entire matrix within those two hash lines, and thus that matrix is no more a matrix but a determinant. How to find the determinant of a 2x2 matrix? Let capital A equal to this idea generic matrix, little a, little b, little c, little d. Then the determinant is, you may think about that as just the crisscross. This only happens for a 2x2 matrix. So it's a times d, then minus b times c. So that's not hard. As a matter of fact, we like when we have a 2x2 matrix and we need to find its determinant. So we'll say here the determinant of A, that's going to be the 1 times the 4, that's 4, then minus the 2 times the 3, so we get 4 minus 6, or negative 2. If we have another matrix, let's say for example, negative 1, 5, 4, and 4. So the determinant here of B is equal to the negative 1 times the 4, so we get negative 4, minus the 4 times the 5, 20, so we get negative 24. So it's nothing there when we have to find the determinant for a 2x2, but what about if we need to find the determinant for a 3x3 matrix, or even larger? We can use the arrow technique, which in this chapter, they don't talk about the arrow technique, but I know some of our friends in physics, they use that. So I would just introduce it here and then just move on. The arrow technique simply says to just rewrite the matrix and then after you do that, the next two columns, rewrite the first two columns. So here, negative 2, 3, 1, 1, 5, and 6. Now, if you notice that when A was that 2x2, we said that the determinant of A was the A times the D, and then it's minus the B times the C. So it's going to be that idea as well. So when we're going, from left to right, we're going to put a plus sign. So we're going to multiply these terms. And then when we go in this direction, we also multiply, but at the same time, they become minus. So like this one, a times the d, we're going to say the negative 2 times the 5 times the 2. Well, that's negative 20 plus, then this is 1 times negative 7 times 1. That's negative 7. And then plus 4 times the 3 times the 6. So that's the 12 times 6, 72. And now we do the minus. So again, this was plus here, and then we do the minus that way. So this is minus 1 times the 5 times the 4, so that's minus that 20, and then minus 6 times the negative 7 times the negative 2. Well, that's just 42 times 2, so that gives us, and it's positive, but it's that minus sign, so it's negative 84. And then the 2 times the 3 times the 1 is 6, but it's minus 6. Now once we add, subtract, combine these, we get just negative 65. So we call that the arrow technique. Well, what if you're asked to do the arrow technique here? Please excuse my coughing. I have a cold. So we have the negative 1, the 3, the 1, the 1, 0, 7, 2, negative 5, 2. Then we rewrite the first two columns, negative 1, 3, 1, 1, 0, 7. So for this one, we're going to multiply in this direction, and we separate with the plus sign, and then we multiply in this direction, and we separate with the negative sign. So here, for this determinant, so that's going to be 0 for that first one, and then minus 5, and then here we get positive 42, the 6 times the 7. So now it's minus, so it's minus here, this is 0, and then it's minus, this is 7 times 5 times 1, that's 35, and it's positive there, but because of the direction, it's negative 35, and then minus 2 times 3 times 1 is 6, and it's minus there as well, and so we do our adding there, we get negative 4. Well, that's probably what you've seen, let's say for example in high school, or in another class. But today our concern is to show how to find the determinant by cofactor expansion. So here we use the method of cofactors to find the determinant. The definition consists of what's called the minor and the cofactor. So let A be a square matrix. The minor of entry Aij, that's just an entry in the matrix, is denoted by, we're talking about the minor. We have the minor leagues and the major leagues. So here the minor of entry Aij is denoted by capital Mij. And it is the determinant of the submatrix found by deleting the ith row in the jth column from the matrix A. Its cofactor correspondent of that for entry Aij is given as capital Cij, and it's equal to negative 1 raised to the I plus jth power. That negative 1 is only going to give us the sign value, positive or negative. Then that's times the minor. Okay. Now look at this chart for the sign value for those minors. So the negative 1 to the I plus j is either positive or negative 1 based on the position of the entry there in the matrix. If the entry is an even position, then it's just the plus 1. If it's an odd position, then it's going to be negative 1. And I just put the signs here just to kind of help you out. Plus, minus, plus, minus, plus, minus, plus, minus, plus. So, you take, we're going to take that sign, positive or negative, times the minor, and that gives us the cofactor. Now, the determinant can be found by what's called cofactor expansion. We'll look at that. So, the definition for the determinant based on cofactor expansion. So let A be an n by n matrix. That's the same thing by saying that A is a square matrix with n rows and n columns. Then the determinant of A can be determined by cofactor expansion in the following way. And that should be in the following way. It won't let me correct it. It's on pen, right? And my computer is having issues, so if I correct it, it'll probably crash, I tell you. So anyway, but that's supposed to be not is, but n. S is supposed to be an n. So here the determinant of A, using this, is equal to, here I'm expanding along the first row. So this is AI1 times its cofactor. So basically it's the entry in the matrix times its cofactor plus all the way to n times. You can do that with any row. As a matter of fact, you can expand along the column. It doesn't matter. So you can expand along the row, any row, to find the determinant for cofactor expansion or for any column. You get the same result. So that's the good thing there. The determinant of an n by n matrix can be computed by multiplying the entries in any row by their cofactors and then adding the resulting products. I'm going to do all that in just a moment. So here the cofactor is equal to the negative 1. This is just one cofactor. Negative 1 times or raised to the I plus j power times its minor. Again, that negative 1 to the I plus j just denotes the appropriate sign, whether it's going to be positive or negative. Here for this example, find all minors and cofactors for the matrix A. So let's look at that. So we're going to first find the minor. I'm going to find M11. The minor is said to be found by deleting the ith row and the ith column from the original matrix. Well, here, if I'm looking for M11, that means that I want to delete the first row, first column. So what I have left is this submatrix, that's the determinant. So I find that, so this is 28 plus 1, we get 29. So now, let's find M12. That is, delete the first row, second column. So I have left 6, -3, -1, and 4. So here we get 24 minus 3. We get 21. Now we find M13. So that means we delete the first row, the third column. And we write what we have left. So this is 6 plus 21. So we get 28. Did you say 27? Thank you. I heard you all the way through the grapevine. Appreciate that. So now, M21. So that means delete the second row, first column. We have left here 2, 3, 1, and 4. So this is -8 minus 3, -11. What about M23? Delete the second row, third column. We have left 1, -2, -3, 1. And so that gives us the 1 minus 6. We get -5. So now move to the last row. So this is M31. Delete the third row, first column. So we have -2, 7, 3, -1. So that gives us 2 minus 21. We get -19. Okay, so what about M32? So delete the third row, the second column. We get 1, 6, 3, -1. So this is -1 minus 18. So we get -19. And then the last one, M33. Now, all we're doing is finding the minors. So this is 7 minus a -12 is 7 plus 12. So we get 19. So now after that, they want us to find the cofactors, and the cofactor just consists of the minor with the appropriate sign, plus or minus, based on the position, right? So we have C11. Now that M11 was the 29, so C11 would be 29, because the sign is going to stay using this for the sign nomenclature. Then C12 is based off of M12. Now M12 was 21, so this is going to be negative 21. See that? Then C13. C13, that comes off of M13. M13 was 27, so this is also positive. It's going to be 27. C21, well, whatever that was from the minor, and I probably could have written it like that, I'm sorry, negative 1 times the minor of M21. How about that? So M21 was negative 11, and then times that negative, it's going to give us positive 11. Right. And then C22, this is based on, again, that sign is positive. It's based on M22, and M22 was 13. C23, we're going to negate M23. M23 was negative 5, so this is negative times negative 5, right there. So that's positive 5. And then C31, it keeps the same sign as M31, because it's even position. 3 plus 1 is 4, right? So that stays the same. That's just negative 19. C33, it's going to negate this 32. It's going to negate M32 because of that. So M32 was negative 19, so this is positive 19, negative times that. And then C33 keeps the same sign as M33, and that's just 19. Okay. Now, when you have that, you can use any of those rows or any of those columns to find the determinant by cofactor expansion, and that's the next problem. Let's see. So that's the same problem from up above. So here they say, well, just use cofactor expansion and find the determinant. Now which row do you choose? It's up to you. Which column do you choose to expand? The rows are probably easier, but sometimes it just depends on the matrix. Finding the determinant by cofactor expansion along a column may be easier. So I'm going to expand along the first row. So the determinant of A is equal to the entry of the 1. Let me just write it out using that formula. So this is A11 times C11 plus A12 times C12 plus A13 times C13. Now we have all that information, so this is 1 times 29 minus 2 times negative 21 plus 3, that's the entry, that's the A13, then times its cofactor, 27. Now on your calculator, you get 152. Now, what if you wanted to, not all at the same time, but if somebody else was looking for the determinant along the second row expansion, that's fine too. So here, or expand along the second row. Let's see. So here, the determinant of A would be, now that's A21 times C21 plus A22 times C22 plus A23 times C23. Let's just 6 times, look at that matrix. That's 6 times C21. We got that from the previous page. That's 11. And then plus 7 times 13 minus 1 times 5. And you still get 152. So you don't have to, what I'm doing here, I'm not saying you have to find the determinant several times. I'm just saying either way you do it, you're going to get the same determinant. So just work it either along the first column, second column, third column, or first row, second row, third row. No need to do all of them like what I'm doing here. I'm just being a teacher. Right? Now, for that person in the back that wants to expand along the third row, so the determinant of A, this would be that negative 3 times negative 19 plus 1 times 19 plus 4 times 19, and you still get 152. So I'm just showing you either way you do it, you get the same result. So you just do it one time. Okay? Cool. Compute the determinant of the following matrices by cofactor expansion. So here's what I'm going to do. If you notice that there are zeros in a particular row, a particular column, then use those zeros to your advantage, because remember, it's the entry of the matrix times the cofactor. The cofactor is no more than the sign times the minor. So if it's 0 times something, that means that subdeterminant cancels out. So I'm going to expand along the second column. I use those two zeros to my advantage. So the determinant of A is equal to, it's 0 times whatever, that's 0, then plus 5 times this subdeterminant by getting rid of the second row and the second column. Okay. So we get 5 times negative 8, negative 40. So you use this information to your advantage. Okay. Let's look at this one. I'm going to expand. I only have 1 0 there. I'm going to expand along the second row. Okay, so you remember the signs: plus, minus, plus, minus, plus, minus, plus, minus, plus, right? So I'm going to use that. So along that second row, at first, this one is going to be negative. So it's negative 1. So I'm going to delete its row and column. So this is 3, negative 3, 1, and 5. And then I come over here to this negative 4 times that negative. That's going to be plus 4 times deleted row and column. So this is 3, 3, 1, negative 3. So this is negative 1 times 15 plus 3. And then this is 4 times negative 9 minus 3. So this determinant is negative 18. And then this is minus 48. So this is negative 66. Well, there are some very neat properties for determinants. Here, these properties are connected with the idea of a triangular matrix or a diagonal matrix. Really cool theorem, which simply says that if a matrix is triangular, that means that if it has all of its entries along the main diagonal, above the main diagonal, and zeros below the main diagonal, that's an upper triangular matrix. Or it could be lower triangular, where you have zeros all above the main diagonal. You have entries along the main diagonal and entries below the main diagonal. So there, if it's triangular or if it's diagonal, that is, a diagonal matrix only has entries along the main diagonal, 0 entries above and below the main diagonal. So if you have a triangular or a diagonal matrix, then the determinant is simply the product of the entries along the main diagonal. So that's pretty straightforward, cut and dry, and I don't think there's any room for error. So let's say if this is matrix A, let's claim this to be matrix B, claim that to be matrix C. Well, matrix A is a diagonal, matrix B is a diagonal matrix. So here, the determinant of A is equal to the entries along the main diagonal. That's just negative 1. The determinant for B, since it's diagonal, is the entries multiplied along the main diagonal there. So that's just 2 times 2 times 2. We get 8. And then the determinant for C, well, C is upper triangular. Again, the determinant is still the entries multiplied along the main diagonal. So that's That's 1 times 2 times 3 times 4. That's it. No more fun. Thank you.